Sometimes with vectors, we add them graphically with a perfect scale, and sometimes we add them to a proportional scale, but we should try to draw them to scale. Okay, did we talk about that a little bit? Right, if I have an object that travels 10 meters and then 2 more meters, is that drawn to scale? Oh, yeah. No, it's not drawn to scale, right? Because the 10 should be a lot longer than the vector that represents 2 meters, right? They need to be drawn with an appropriate proportion. Okay, so when we say they're drawn to scale, we have to actually try to do our best with that. So this might be 10 meters and this might be 2 meters, right? That gives us a little more accurate representation of what's supposed to actually be happening in our motion. Okay, so we draw them with some sort of scale. Sometimes we'll get out a ruler and we'll actually draw them to a legitimate scale, which means like I might say every centimeter on my paper represents 10 meters, right? Or something like that. We'll get out an actual a ruler and do it that way, but not a lot. Most of the time we just are able to draw them with a pretty simple diagram. Okay, we draw all vectors with what's called the tail to tip method. Tail to tip method. So when we look at drawing our vectors, first and foremost, we draw them with an arrow. Okay, we represent them with an arrow. And I think that was on one of our last slides, but I want to write it again. Represented by an arrow. Okay, so when we draw vectors, we draw them with an arrow. And we add them using what's called the tail to tip method. So I want to just kind of demonstrate what that means. When I draw a motion diagram, I'm going to always start with my origin, right? I'm going to start with my origin. And so let's just draw my origin right there. Let's say that I walk east, then I walk south, then I walk east some more, then I walk north, then I walk west, south, east, right? Let's say I make this whole zigzagged pattern. Here is where I'm ending up, and here is where I'm starting. Okay, this diagram right here is me adding those vectors tail to tip, one right after the other, right? The tail of one vector, which is the back side, to the tip of the next one. So tail to tip, right? The tail of the second goes to the tip of the first. And so we just keep adding them one right after the other. The opposite approach would not work as effectively, okay? Because if I tried to draw this same motion all from the origin, then south, then east again, then north, then west, then south, then east, right? If I don't draw them one right after the other, this doesn't show me anything about my motion, right? This is me just drawing all the vectors from the origin. This isn't taking me anywhere. It's pointing me in a lot of different directions, but it's not taking me to my final destination. So we have to add them one right after the other. That's really important. Okay, we add them tail to tip. The tail is always at the starting point of the motion, and the tip always goes in the direction of the motion. So if my motion is to the west, let's say this. Let's say that I went 10 meters west. What direction should my vector go? To the right, to the left, up, or down? Left, right? West is this direction, so this would be 10 meters west. All right, does that part make sense? Or we feel okay about the cardinal directions? Cardinal is northeast, south, and west. Okay. So we have the vocabulary term already that we've kind of looked at called resultant vectors. What's it mean to be a resultant vector? It's the sum, okay, or more specifically, the graphical sum of all of my vectors. Okay, the graphical sum of my vectors. And so that means it gives us kind of an overall picture of where we are from where we started, okay? So the resultant vectors are graphical sum. The resultant vector is always drawn from the origin to the tip of the last vector. So the resultant vector is not drawn tail to tip, right? It does not get added on to the rest of them. So let me give you an example of a resultant vector. Let's say I do my walking path again. I go east, south, east again, right? I go over here, then I walk north, then I walk east, then I walk north again. Okay, let's say I walk this whole path, and I end up at a location way over here. My resultant vector now is going to be drawn from where I started to where I ended, right? This vector right here is called my resultant vector. It's showing me my precise location from where I started to where I finished, okay? So the resultant vector is really showing us here our displacement. Remember, displacement is how far we ended up from where we started. Okay, can you remind me of the difference between distance and displacement?
Distance is like how far you've traveled
Mm-hmm.
in total, and then displacement is just how far you are from the origin.
Bingo, right? Distance would be the total sum of the length that I've covered. So here, if I made up numbers, right, I'm just going to call this 2, 1, actually I shouldn't do that, 4, 2, 2, 2, 8, 1, 2, 3, right? I would add up all of those different values and that would give me my distance. But my displacement, I would have to solve for how long that purple vector is. And to do that, I'm going to have to start using some trig functions, right? I'm going to have to draw a triangle that goes with that. I'm going to have to find out what these sides are in order to find out what that hypotenuse is. And that's what we're going to start practicing today. We're going to figure out how can I solve for that resultant vector? How can I figure out how far I am from where I started? So that's what we need to know about the resultant vector. The resultant vector you always get to start over on the resultant vector and go from your origin to your last vector. Okay, so let's look at an example here. All right, the runner starts at the origin. You can go ahead and draw this as we're doing it as well. It starts at the origin and runs forward 2 meters. So which direction would we consider forward, do you think? Positive x. So to the right. So 2 meters. There's my first vector. Then he runs backwards 6 meters. So am I going to start over at the origin and draw it back 6? No, I'm going to start right from where I was. So I was at the 2 mark. I'm going to go backwards 6. Then he's going to run forward 4 meters. So I'm now happen to be back to where I started, and then forward 5 meters. So there's where I'm at right there. So my ending point is right where I put that x at the end, right? That's where my ending point is. So if I were to ask for a resultant vector, you can draw it either on top or just like slightly underneath. But that purple vector would be considered my resultant vector, right? Because I'm 5 meters to the east from where I started. And that would be the same as my resultant vector. Does that kind of make sense? What would be the total distance I covered here? If I asked you for the total distance I covered, what would you tell me? 17 meters. But my displacement, so my distance is 17. My displacement, however, is 5 meters east. Okay, or forward in this case, right? We drew it on the east axis. Why do I not have to include a direction with distance? Any thoughts? Why do I not have to include a direction with distance? Good. It does include how far, but do I go all the same direction for my distance? I go multiple ways, right? I go forward and backward. So I can't label a direction if I'm going multiple ways. And distance just doesn't need a direction, right? It's the total sum of our length. Okay, let's try another resultant vector here. Let's say that I travel 11 kilometers north, then I travel 11 kilometers east. Actually, I want to change this question actually right away. I don't like it to be a 45-degree triangle. So I'm going to try 11 kilometers east, then we're going to call it 8 kilometers east. 11 kilometers north, then 8 kilometers east. So change that on your notes because I want this to be a little bit different practice problem. Okay, so I'm going to start on my origin, and I'm going to go 11 kilometers north. Do I have enough spots on my graph to make each one of those worth 1? No, so what do you think the scale of my graph needs to be? I think I can go by 2s, right? Here's where I'm starting at. 2, 4, 6, 8, 10, 11. So I'm going to go actually past a little bit. So I'm going to go 11 kilometers north. Then I'm going to go 8 kilometers east. So I'm going to start over at the origin and go like that. Is that what it's going to look like? Okay. I'm not going to go... Oops. I'm not going to go north, then start over. I'm going to add them tail to tip. Okay, so I've got to make sure that I'm going up, then over. Because my resultant vector, which I'm going to draw next here in red, that has to take me from the origin to my final location. Does that make sense? My resultant vector is the one that's in red here. That has to take me somewhere. Okay, it's got to show me where am I going as compared to where I started. So here's my 11, and here's my 8, okay? Kilometers. So if I want to find the resultant vector, I need to figure out what's the side of that triangle. How How far am I actually from where I started? So how could I go about solving for that? Yep. A squared plus B squared equals C squared. What's that called? Pythagorean Theorem. So let's go ahead and do that, right? I'm solving for the side C here, okay? So you're going to need your calculator out, and we're going to go ahead and solve for that side. All right, in my calculator, since I know I want C, I'm just going to go square root of 11 squared plus 8 squared, and that's going to give me my answer right away. 13.60 kilometers. Is that what you had when you plugged it in? We are going to end up, my resultant vector is 13.6 kilometers from where I started. Okay, my distance walked would have been 19, but my displacement is 13.6 kilometers from where I started. But that's not an exact enough answer, because if I want to end up 13.6 kilometers from where I started, and that's all the information I give, couldn't it be 13.6 kilometers in that direction? Or in that direction, or in that direction, right? I've got to tell them what direction to go, okay? And so is northeast the area, the direction that we're headed? Yes, but unfortunately, northeast is not exact enough. I have to give them the angle at which to leave our origin, okay, so that we can end up in the right spot. So I need to not only find the hypotenuse of that triangle, I have to find the angle that touches the origin. Okay, so do you remember your trig functions? SOHCAHTOA? If you don't remember those, you might want to write that down, okay? If I want to solve for this angle right here, okay, I have available to me the side opposite of that and the side adjacent to that angle, right? What's adjacent mean? It means next to. So if I have this angle, I know what the side is that's next to the angle, that's 11, and I know the side of my triangle that's opposite it. Now, I do technically have my hypotenuse because we just solved for that, right? But I don't like to use the hypotenuse in this calculation because what if I solve for the hypotenuse wrong? Now my angle's wrong too, right? So I like to just use what I'm given. So if I have the opposite and the adjacent side, that means I'm going to use tangent, okay? So the way I would set up this equation, I would say tangent of my unknown angle is equal to my opposite side over my adjacent side. Okay, so it looks like this when it's regular. Tangent of theta equals opposite over adjacent, right? Theta is my angle. So, if my goal is to solve for the angle, I need my question mark. In your calculator, you're going to use the second function of tangent. Okay, or the, I don't know if they call it the inverse tangent. I don't know what it is. But it's the second tangent. So you're going to hit second tangent. So it'll come up like this. Tangent minus 1 and then a parenthesis. That's what it'll look like in your calculator. And you're going to plug in opposite divided by adjacent. So 8 divided by 11. Bless you. So I'm going to do second tangent of 8 divided by 11. And that gives me 36.03 degrees. We're close to finishing our answer here, but now we're at 36 kilometers at 36.03. I'm just going to leave off that 03. We're just going to call it 36 degrees. Now, I can't just say northeast, and here's why. I can't just say northeast because if I'm looking at my, if I'm looking at my coordinate system, I have a 36 degree that's here, and I have a 36 degree that's there, right? This could be 36 degrees, or this could be 36 degrees. We have to tell them which one it is. Okay? So I want to go back and look at your triangle that you built. Okay? Look at our triangle that we built. We've got to decide, are we 36 degrees north of east, or are we 36 degrees east of north? Those are our two options, right? North of east or east of north. Do you have a guess? Okay. I want to show you how we know the difference. We're looking at this angle right here. The way we can tell is we have to decide which axes is it touching. Which axes is my angle touching? The north, the east, the south, or the west axes? Yeah, it's touching the north axis, right? Isn't that north right there? Okay, isn't this angle touching that north axis? Yes, it is, right? Here's north. This angle right here is touching that axis. So then I decide, is my triangle swinging east of north or is it swinging west of north?
East.
My triangle swinging east of north. And so that's how I find out my final angle there, east of north. So that right there would be my final answer. 13.6 kilometers at 36 degrees east of north. So there's a lot that kind of goes into that final answer, right? For us to be able to figure out where we are from where we started, it takes a lot of that work. Okay? Tell me what questions do we have about that part?
Do we have to use the SOHCAHTOA like in every problem?
Not every problem. Only when we have things that are moving, like not in the same direction, not on the same axis. So if your object is just moving east, then west, then east again, then west again, right? Then it's just a forward-backward situation. So you don't have to find an angle. The times you need to find the SOHCAHTOA and use the angle is when we've got things that are moving north and then west, or east and then south, or whatever, when we have got things moving in two dimensions, right? X and Y. Does that kind of make sense? So if your displacement ends up with some sort of triangle, then you do. But if my displacement just looked like I went west and then I went east again, then I went west, right, and I end up here, well, now my displacement is simple, just 2 meters east, right? You don't have to use the angle there because I didn't need to build a triangle there. Okay?
How can you